Thanks a lot. Thanks for the invitation to be here and to enjoy this amazing meeting. And I will not explain, to save my self-embarrassment, I will not, first of all, I will take this. I will not explain the title, but I will touch it if it will come during the questions. I'm going to present a rather conceptual idea today that, if true, it should provide us an island of sanity in the complexity of shallow cloud fields that we learned so nicely this morning, how complex and how important they are. I want to acknowledge friends and students that I will compile part of the work that we did together. So Graham, you all know him, he's here without the earphones. And Ellie helped us with the nonlinear dynamics, thinking about the nonlinear dynamics, and the rest are people from my group. Especially I'm going to show stuff that Tom, she's about to graduate, and Juan, she's a postdoc, are doing. So the open to close case that we've heard about so many this morning by all speakers is our model organism. So if you want to think about bifurcation, if you want to think about two states that can coexist under similar conditions, so give me the same thermodynamics and play only with the aerosol concentration, and I could get either closed or open cell scenarios, and we can play with other controlling parameters as well. I want to extend the view of this model organism to other cloud types, providing, as long as they are shallow for now, and as long as they are well organized. So one important parameter that I will try to push is that organization. If we see high level of organization against entropy, it means a lot, and we can use it. So in this case, you can see shallow cloud fields forming over the Amazon. And usually when we think about the Amazon, we think about deep tropical convective clouds. But actually during the morning, during most of the year, such shallow clouds form. And I hope that you could see that they are highly organized. They are very sensitive. So basically you could see the Amazon River by the absence of the clouds. And they form every day, cover thousands of square kilometers. So it all started with our toy model many years ago. And Graham described this toy model. It looks extremely innocent. So two ODEs, what could go wrong? One for the cloud depths and one for the droplet concentration, very innocent. Let's play with it. There is only one caveat. There is a delay in the sync term. Now, for anyone who did not play with DDEs, delay differential equation, it's a whole new game, okay? The level of complexity is on the same level of partial differential equation. So basically one DDE equivalent to infinite amount of ODEs, describing all the initial condition along the delay line. And finding analytics for such equation is very challenging and beautiful. We played with these equations and we tried to simplify them, and eventually we came with this very distilled equation that Graham have shown some results of, we replaced all the parameters, or most of the parameters, by one non-dimensional parameter. So it's very elegant. And we have basically two parameters, so the non-dimensional mu and the delay. And with this, we could describe a series of states that the system could choose to be at. I just want to say that later on, we replace these equations with the infinite amount of a series of ODEs, showing that indeed we see Hopf bifurcation, and it's a clear classical Hopf bifurcation and limit cycles, and everything really works, so we can use the machinery of bifurcation, or the knowledge gained in bifurcations studies, to study such toy model.
One quick question.
Sure.
Could you mention which parameters enter into mu?
Yes.
What physical information enters into mu?
Sure. Everything, basically. But
so
here,
sorry, I'll just repeat the question. So the question is, what enters mu, right?
yeah. So n, this is mu. This is the equation for mu. N represents the droplet concentration. Tau represents the characteristic time for cloud recovery. So once you depleted the cloud, how fast the cloud recharge. So it's a recharge characteristic time. And H0 represents the potential, or the maximal depths of that the cloud could approach to. Okay? Sure. And alpha is, of course, gaining all the units together. So the bottom line of this toy model brought us to two non-chaotic states. So basically, we have steady state and we have oscillations. And Graham discussed a lot about the steady state and the oscillations, and we celebrated the oscillations because we could, in very simple mean, explain the reorganization of the open cells and why they are dancing, and how rain, what is the role of rain playing in this reorganization. But the steady state is kind of intriguing concept for clouds. We know that clouds are dynamical systems, and we know that they need convection. So what do you mean steady state? So in our toy model, it means that we have a perfect balance between source and sink. So we have a machinery to recharge the cloud due to instabilities, and we have drizzle or evaporation, and there is a perfect balance between them. But is it applicable to nature? So we moved to data, and we developed means to do Lagrangian analysis. And this by itself is kind of surprising because clouds are changing all the time. So how would you do Lagrangian analysis? What would you follow? So apparently, the characteristic time for changing of the cloud field is supposed to be much slower compared to the characteristic time of the snapshot or the sampling rate. And if so, there is still a lot of similarity that we can follow. And this is what we were doing, and we used geostationary satellite to follow cubes of such fields. And we are showing that indeed it converges and the similarity is well maintained. And then we move our analysis to the post-Lagrangian correction. So basically, as if there is no advection. And now we are following the same cell throughout the day. So this is one snapshot of open, and this is one snapshot of closed. And if our Lagrangian analysis indeed works, we follow them in time, and we see that the closed cells maintain the same cell for many hours. So we can follow the cell for 9 hours. Why 9 hours? Because we use the visible channels. But actually, we can follow the same cell for a few days. This is kind of mind-boggling because it's 5-kilometer convective cell. It's supposed to live 1 hour. We follow it for 20 hours, for 40 hours. Okay, so there is a locking, there is a mode lock here that we can enjoy. And of course, we see the dancing of the open cells that behave more like they're supposed to. And if we do Hofmöller, we take one slice of this Lagrangian corrected data set, we see that the closed cells have solid ridges that we could follow throughout the day, while we see the oscillations of the open cells. So the metaphor of our predator-prey model, and I would not call it predator-prey today, I would call it various host, but I will be happy to discuss it later in the question time. Our model really can describe, in essence, the two states. Good. Let me do a stop here and talk more about the Lagrangian Hofmöller space. So suppose we have a field of closed cells, and suppose that we correct the Lagrangian movement perfectly, and then suppose we draw one column of each snapshot along the time. So we create the Hofmöller, and the Hofmöller will translate to straight lines. If we are correcting the Lagrangian correction works well, and if they are in steady state. Okay? The beauty of this Lagrangian Hofmöller space is that even if we have tilted features, it will still be parallel to the time domain, and also, even if we have less regular structure, as long as the two conditions, steady state and correct Lagrangian analysis, it will translate to lines. So this is a very nice measure trying to detect steady states. Okay? If we have oscillations, we will see the oscillations after the corrections. So the Lagrangian Hofmöller maps dynamical features to lines if there is a steady state. And now we want to extend the concept to other cloud type. And our first choice would be cloud streets. So I'm very happy that it was mentioned before, a question about cloud streets. So this is a snapshot, a photo, airplane photo of cloud streets. And cloud streets are, it's a very common feature, usually coming from cold terrestrial air that goes over the ocean, but not necessarily. And basically you can think about it as a roll solution of Rayleigh-Bernard convection with a lot of complexities, additional complexities of the cloud. Okay?
On this picture, what direction is the wind?
Okay, good. This is exactly what I'm going to. Thanks for the question. So the beauty or what's special about cloud street is that the streets are along the wind direction, unlike gravity waves. So if you want to distinguish between gravity waves are normal to the wind direction, and cloud streets going with parallel to the wind direction. Okay? Okay, and you can see in this zoom in case of cloud streets that actually cloud streets are very close cousins of closed cells. I would call them closed cells. And if they are closed cells, they should be in steady state. Another set of clouds that I want to discuss today are these shallow convective clouds over the Amazon. So here you see the whole diurnal cycle, and you see they form early in the morning, they peak during noon, and then they start to cluster to deeper convection. Okay? And if you look carefully on these cloud fields, first of all, they are beautiful, but also you can see citation of streets. So we call them green cumulus because we've seen that they are really, really common throughout the world. But also you could see streets. So these are terrestrial kind of cloud streets. And this is you can follow the direction of the advection. So it's beautiful. And to convince you that they are very common, this is a study that Tom did over 3 completely different methodologies, theoretically. And basically, if you zoom in and you look on the cloud, you would not know which came from where. So it's really common, and they are affiliated to vegetation. That's why we call them green cumulus. Okay, so now we move to playing with data. We take geostationary data of cloud streets, of green cumulus, of close and open. We do Lagrangian correction. I hope that you will believe me that I know how to do Lagrangian correction. And as a first kind of idea, the upper row is just a snapshot of closed streets and green cumulus. The lower row is average of 100 snapshots. So think about it. We think about clouds and they are emerging and dissipating and so complex, but still you average 100 snapshots and you see a lot of structures. So this is kind of a first approximation, indication for steadiness. Okay, it's not perfect.
It's a Lagrangian average?
Sorry?
It's a Lagrangian average?
So we did Lagrangian correction, and then for each snapshot, we just took for each box, we took the average.
How far are the snapshots spaced in time?
Sorry?
Yeah, no, if you take 100 snapshots right away, they will all look the same.
Cycle,
so what is the distance?
8 hours.
8 hours?
Yes. Well, I won't swear it's between 5 to 8 because with the green cumulus, we don't have 8 hours. So it's between 5 to 8, okay? So it's a lot. And we have a snapshot, a ghost snapshot every 5 minutes. So try to imagine you maintain such a clear structure, averaging 100 or so snapshots. So you could feel the steadiness. And if we do the Lagrangian Hofmöller analysis, we start to see, so the closed, we did it already. We see the ridges. The streets, I think that it's very convincing that you see the ridges. The green cumulus, okay, you see kind of a hint. Wow, okay. But we need to study more, so I'm running. We move to the modeling space. We are lazy, so we take one scene for which we have many relevant cloud cases, the east coast of the US, so half of the North Atlantic. This is another satellite image, and here you see the classics of close to open. So you see that the upper one, so first of all, the measure is updraft, vertical velocity, and on the above open, you see that the updrafts are along the walls and the downdrafts in the middle, and exactly the opposite for the closed. So this is a textbook example of close and open. So now we can describe the whole field by means of other variables than reflectance. So we have the vertical velocity, we have the buoyancy, we have the convergence, we have the divergence, and we can do the same analysis to all of these fields. We are doing the same for the green cumulus. So this is a satellite image, and this is the output of our model. And if the model is able to create the pattern formation, it's quite convincing that it catches the dynamics. I don't know, and I will not swear about the microphysics. Actually, the microphysics is likely to be wrong, but it catches the dynamics. And we can see very great similarity. And again, let me run. So these are the analysis. We took the open cells to show you a counter example. So this is a counter example of the Hofmöller space, and you can see that there are kind of triple junctions, and that we cannot see equivalent lines. These are the cloud streets over the ocean. I think that it's very convincing. And these are the green cumulus. We see features, we see worms. Sorry for using it again. We see worms that are taking along 5 hours, 4 hours. So they want to be in a steady state. Of course, over the terrestrial regime, the fluxes are not uniform, the topography is not uniform. You have many barriers, but they want to be in a steady state. And I will move to the summary. So we have extended the concept of convective steady state to other high organized cloud field. Such cloud systems cover large, so they are extremely important with respect to radiation, but as it was presented before, cloud feedbacks. We don't understand the shallow cloud feedbacks to climate change, and we need to understand better. The convective steady state can use to validate the output of models, but it could be used as another constraint for climate models. And I would ask the climate modelers how to use it. I'm not, but it's definitely a very strong constraint, and it serves as an additional island of sanity. So out of this sea of complexity, suddenly we have a steady state, a dynamical steady state. It's beautiful. We have something to catch upon. And do I have another half a minute to show something? Okay. Just to show you how rain kills the party. So these are cases that we study over the Mediterranean, and these open cells are deep open cells. So it's not the open to close, it's not marine stratocumulus. Each cell here has the thickness of 5 kilometers. So we are talking about post-frontal deep clouds. We are talking about free atmosphere cloud, and still we see cloud streets turning to form open cells. And let's see the role of rain in this organization. So, okay, the green contours are contours of rain. I don't remember the number, but significant rain on the surface. And we see a divergence, convergence. So if it's a negative divergence, it means convergence. So the clouds would form along the red line, the red stripes. So we see cloud streets, and we see here that the cloud streets start to break. And watch the movie. And follow the green contours. Oh, come on. Sorry. So look on these green contours and see how they create triple junctions. Basically, they break the steadiness, and after a while, they create open cells. They trigger the formation of open cells. Thank you very much.
Okay, open for questions. Michel.
It's really impressive. In engineering, when we do Rayleigh Bénard convections and such, we talk about Rayleigh numbers, Richardson numbers, etc. Is there any chance that we could have an estimate of where in the phase space of those numbers these phenomena occur?
Yes. So we are trying, and there are many attempts to define the Rayleigh number of the problem. I would say that the Rayleigh number is about the critical, but not too high, few thousands, but it depends, it's really case dependent. So the thick atmosphere Rayleigh number would be completely different to the shallow atmosphere. So but basically the reason why I called it near the bifurcation point is because we see really well-behaved, low Rayleigh number organization of the convective cells. And then we see additional feedbacks that are could not be described in a Rayleigh-Benard system because these are additional phases that we have to deal with that break the organization as Graham described, rain, evaporation, basically decouple the clouds from the feeding tube, creating opposite dynamics, encouraging the nearby formation of clouds and so on. So as a first approximation, we have attempts to use, if I would teach cloud physics course now, I would start with Rayleigh-Benard. This is really the basic of everything. And then put the other phases.
I can strongly agree with that statement, Ilan. Yeah.
So,
Other comments, questions? Eberhard.
yes.
Yeah.
So, so in Rayleigh-Benard convection, when you incline a system, so you get a shear flow, which you get here, then you get these longitudinal rows. We call them longitudinal rows or transverse rows, depending on whether they align with the flow or are perpendicular to the flow. And in Rayleigh-Benard convection, if the shear gets strong enough, they turn by 90 degrees and are traveling. I have a picture from Ithaca out of my window where I see actually a state like that. So I see both of them. So sometimes these rows that are in the other direction might actually be convectively driven and not just by gravity waves. It's probably rare, but it might happen. Has anybody tried to do something like a Swift-Hohenberg type approach to these type of patterns? I mean, really doing pattern formation with clouds, because clearly the Rayleigh number is, I mean, as you said, it's low, but it's not low, it's gigantic, but in reality, the patterns are completely ordered and seem to be even reproducible, which is amazing, I have to say.
Yes.
Has anybody tried to do Swift-Hohenberg type analysis?
So
and looked at the defects, you know, where these things end and where they change the wave number and stuff like that?
So using the Rayleigh-Benard as a base for clouds were very popular.
I know Busse and
during the 70s.
Yes, Busse, Whitehead, and so on. Yeah.
Yeah, and I think that it was kind of because we all acknowledge that it's not.
No. What I would try to say was that, I mean, these are superstructures, right? So these are the turbulence in the cloud is very high, and so it's not a laminar traditional onset Rayleigh-Benard state.
Right.
But once you have these patterns, you can ask yourself, like we did in Rayleigh-Benard at onset for many, many years in the 90s. You know, we've spent huge amount of time on analyzing patterns like this. I did myself, 10 years, 15 years of my life. Have people tried to do approaches that are basically taking the 2D plan form? There's an equation called the Swift-Hohenberg equation, which is an approximation to periodic states, which probably doesn't describe this, but it might be able to modify it, and then you just describe the 2D plane form and the evolution, for example, during a day by different driving mechanisms and things. Have people tried to do effective models that are 2D? I mean, basically not just time dependence, which is the 1970s in pattern formation. Then later in the 90s, 80s and 90s, we went to 2D plane forms and tried to understand them with some more sophisticated spatial temporal models. Are people doing this already? I mean, are you doing it? That's my question.
I am playing with it, but not to the level that I can show stuff. With Graham, we try to add to the Rayleigh-Benard system also the cloud feedback. And
right, so I wanted to be, to basically go away from cloud physics and just say, here we have a pattern.
So it's a good idea.
And can we describe these patterns with effective equations, which are similar to Rayleigh-Benard, but they're not?
Let's continue this one offline.
I think it would be nice to talk more. Thank you.
Really, really interesting. I think we have time for one more question. If there's Francesca, you can come on up and but if there's one more question, we'll take it.
Okay.
Okay. Thank you again, Ilan.
Thanks.